given any point on a plane, I can identify it with x and y, and that's what you're used to. You're used to doing that. But if you think in terms of this as a vector and this as a vector as a way to get to that point, we just invented a shortcut for that. These are essentially the component vectors of the position vector of this point. The position vector goes from the origin to the point, has a length and a direction that's given by the angle in standard position, and so I can identify that point in either of two ways. The things that link the two together, the way in which the two interact. You know the coordinates of the point are x and y, and we call the magnitude of the position vector r, because it's sort of like the radius of a circle, and you know that the equation of a circle is x squared plus y squared is equal to r squared. So right off the bat, that's the first thing you already know about the polar coordinates, which are expressed as r comma theta, and the rectangular coordinates, which are expressed as x comma y. So all of a sudden, if you know these two numbers, you can get this one. The other thing you know is that x over r is equal to the cosine of theta, and y over r is equal to the sine of theta. So if we multiply both sides by r, x is equal to r cosine theta, and y is equal to r sine theta, which means if you know x and y, you can get r, and if you know x, y, and r, you can get theta. One of the things you need to be able to do is to convert polar into rectangular Cartesian coordinates and back again, both as individual points and as equations.
X and y are Cartesian coordinates?
Yes.
Okay.
And they are called that because the guy who made it up is Descartes. Yeah.
And rectangular is the same as Cartesian?
As Cartesian, yes.
And r theta is polar.
Yes. So the origin is called the pole, and the polar axes look like the Cartesian coordinate axes, and that creates a bit of a problem. You're used to the Cartesian coordinate plane, so you're used to thinking this is sort of positive and this is sort of negative somehow. The top is positive, the bottom is negative. The right is positive, the left is negative. That's true in rectangular coordinates. In polar coordinates, it has no meaning. In fact, if you think of it, in rectangular coordinates, all of the reference lines are either horizontal or vertical. So it's easy to say, oh, good, positives over here, negatives over here, because everything you do is tracing one of those lines. With polar coordinates, all of the reference lines go through the pole. Those are the reference lines that tell you the direction of the position vector. And then the reference lines that tell you the magnitude are actually circles. Looking at a point, there's no way of knowing whether r and theta are positive or negative, because you're dealing with circles here. So you could go either way. That's one thing that's kind of annoying. Another thing that's kind of annoying, if I give you a point on a plane, any point on a plane, there is only one way to express that point in rectangular coordinates. X comma y. No ambiguity at all. With polar coordinates, there is some ambiguity. The distance from the pole to the point is r, and the angle is theta. So r comma theta would be the way to express that just sort of naturally. But as it turns out, there are other ways. For example, I could go all the way around to theta plus 180 degrees, then from here go backwards r steps, still getting to x and y. I could go the other way and then just give you r, and that would get me to the same point. We're almost done with this, but there's one more weird thing I could do. I could go in a minus direction, theta, minus 180 degrees, and then go negative r. All four of those descriptions using a radius, or a magnitude, and an angle, a direction, describe position vectors that go to the same place. And the problem it creates is that in the xy coordinate plane, you are used to graphing equations, and if both equations wind up in the same place, if they intersect, that tells you there is an xy solution that is the same for both equations. Because there's only one way to get to point xy in the rectangular plane. However, if you're graphing things with polar coordinates, you might look at that and say, oh, look, x comma y, this point right here. Oh, wait, not x comma y, r comma theta. Yeah, that's it, r comma theta. That's where they intersect. That must be a solution to both of them. But that's not necessarily so. Because although x comma y would be a solution to both of them if you had the equation in Cartesian form, if you have it in polar form, any one of these four might be a solution, but not necessarily the same one for both equations. And the third thing is that we're not used to the drawings that come up or what the equations look like. Limesons are essentially circles that either have a dent in them or not only have a dent in them but also have a loop in the middle of them. Aside from just having an inner loop or no inner loop, if this point is on the pole and there is no inner loop, this shape is called a cardioid. They are of this form, r equals a plus b cosine theta, or r equals a plus b sine theta. Another form of equation, the conic sections, these will form limesons as well. The limeson has a loop, the conic is a hyperbola. If it has no loop, it's an ellipse, and if it's a cardioid, then it's a parabola. And of course, you can also make circles and lines using cosine, sine, secant, or cosecant. And there are the roses, the petals, equations that look like these. And that's really enough. It's more than enough. And that's really enough. It's more than enough.